There we go. All right, welcome back, everybody. We are now in section 10.2. And we're going to do a little bit of 10.3 today coming up as well. Okay. So this is going to be our last day talking about trees. We're just going to do a little bit of application, a couple of examples of what you can use a tree structure for. Okay, so we're going to start with a thing called a binary search tree. Oh yes, sorry, we're not in chapter 10, we're in chapter 11. Thank you. 11.2 and a little bit of 11.3 today. That's what I meant to say. Thank you. All right, so let's say you've got some data. Let's make a string, a random string of data. Like this a randomly organized, just a randomly arranged list. Okay. We don't necessarily want this to be ordered. Having a random arrangement is going to be better. And then we'll talk about how to improve the structure later. But let's just do letters. And so I'm going to just do a random string of letters like K, A. Do we want A? No. K, K, H, B, N, A, J, W, C, M. Okay, something like that. So fairly random string of letters. So a binary search tree is a structure in which you can store ordered data. Okay, so ordered in the sense that you can, determine the order between them. Okay, you have some sort of ordering that allows you to, it has to be a total order, which allows you to compare any two elements and say which one comes first and which one comes second. Okay, so it's the binary search tree is a tree structure in which we will store this data in a way that makes it easy to search and retrieve elements from the data set. That's sort of my understanding of what you would want to use it. But I'll explain how we're gonna do it. What we're gonna do is we're going to create the structure, the tree structure, starting with a root. Okay, that's going to be our root node right there. And then we are going to read the data from the string. Okay, this can be, think of this as sort of like an input stream. We're going to read the data, right? And then as we read the data, we will insert the data into the tree according to a very specific pattern. So the very first thing we read is going to go into the root of the tree. And then from there, we will construct the tree by either going left and creating a left child or going right and creating a right child. And we're going to sort of do that iteratively for these, for these children. Whenever we create a child, it can have left and right children like this. And the result is going to be a type of tree called a binary tree. Remember, binary tree is one for which every node has at most 2 children. Okay. So we're never going to have 3 children or 4 or any more than that. We could have 1. We could have a situation where it doesn't have to be like fully fleshed out. There could be areas where like, oh, there's only 1 child over here, and then over here there's 2, but then this only has 1, and then that has 1, and that sort of thing. So, also we are gonna be keeping track of whether each child is a left child or a right child. And so for the purpose of this tree, If the arrow goes diagonally to the left, it is going to be a left child. And if the arrow goes diagonally to the right, it's going to be a right child. And it's important to keep track of whether you have a left child or a right child. So that means that in this tree diagram, we're going to add on this extra rule that that type of arrow means a left child, and that type of arrow means a right child. Okay, so it's not like the usual tree structure where you, or graph structure where you can like move things around and it's still the same exact graph, right? In this case, the direction we're going matters, and you would label them separately, left or right. Okay. So now, what determines whether we go left or right to insert, whether we put, so basically when we want to make H, we read the next thing in the string. We want to make H a child of K. And either it's going to be a left child or a right child, depending on whether H is before K or after K. The ordering that I'm using is just alphabetical order. H comes before K in the alphabet, so we will insert H into our tree structure as a left child of K. Make sense? Then we read the next element in our stream. We have a B. You always start at the root. You always begin at the root. The root is like our access point for the data structure. Okay, we access it from the root, and then, but the root is already full, right? The root has an element stored in it. That's called the key for that node. The key is sort of the data, the piece of data which is assigned to that node in the tree structure. Since that root already has a node, we then ask, is the new datum, right? Is this new piece of data that we're reading, is it like before or after that, the key for the root? So is it before or after K? B is before K, so we would go to the left. And then we would see that, that child also is already assigned a key, right? That child is already assigned H. So then we ask, is B before or after H? It's before, so we would make a child to the left. There we go. There is no child node there already, so we create a new one, and we insert B into that node. Assign that node the key B. It's making sense so far? And then we will continue. For each new entry, we start at the root and ask, is it to the left or the right? N is to the right of K. It comes after K in the alphabet, so we go over here. And we didn't already have a node there, so we create a new one. So now K has both a left and a right child. That root is not allowed to have any more children. Okay, so anything further that we add into this tree is going to have to end up down here somewhere. Okay. We add in A, next we read in A, we bring A in, A goes left, A is before H, so it goes left, A is before B, so it also goes left, and it ends up over here. And we can just read in, continue reading in like this, A, H, I, J, K, so J is before K, but after H, so J goes here. W is after K and also after N, so W goes over here. C is before K, before H, but after B, so C goes over here. And then M is after K, but before N, so M goes over here. And there we go. So now this thing is a binary search tree. This is data stored in a binary search tree, which is abbreviated BST. And now the reason we like this is because if you want to retrieve something from this data set, you can start searching for that element at the root. And the algorithm is like, hey, look at the root. Is it equal? Is the root the thing you're looking for? If not, ask, is the thing you're looking for before or after the root. So for example, if we're searching for J, right, we would start here and say, is K J? Nope, it's not. J comes before K, so we go left and we look at this node, H. Is H J? No. J comes after H, so we go right. Is that J? Yes. We've retrieved the data, right? Are we looking, say you're coming in here and you're looking for Z. Let's do Z in a different color. Say you're looking for Z. Is Z in this data set? You start here. Is K Z? No. Z comes after K, so you go this direction. Is N Z? No. Z comes after N, so you go this way. Is W Z? No. Z would come after W, so you go this way, but there's nothing there. So then you could say, aha, Z is not in the data set. And that was a fairly quick, it was pretty fast to check whether or not Z was in the data set. We only had to check 3 things, 1, 2, 3, and then we ran out, right? We never had to check these ones over here. And the benefit of this data structure is that you don't have to check those over there, because we know that the way this data is organized, Z would appear right here. It has to, because if the data is organized following the rules that we've laid out here, the like left-right rules, it would have to be here, right? But it's not. So it's better than just having like an array or a list, or, you know, because with a list, you just have to search through the list until you find something. Well, that's not entirely true. There is a binary search algorithm that you can use on a list, but the list has to be ordered. In this case, we've sort of built in that binary search kind of algorithm to the structure of the data itself, which, you know, explains the name binary search tree. Okay. Now, it's possible that when you create a tree in this way, you might get a tree that is not well balanced. If it's not well balanced, then it's not a very useful data structure. Say, for example, we were using an ordered list, A, B, C, H, J, K, M, N, W, right? If I took the same set, but I had it in alphabetical order, then when I start creating my tree using the same algorithm, it ends up looking like this. This is terrible, right? It's W at the bottom. Okay, I got a little messy down at the bottom there, but you get the idea, right? It's like this ends up being a terrible tree structure. It's not a useful binary search tree because it's like not balanced at all, right? This is no better than a list. If you were to try searching, you would still have to just search through the list in order, right? So having a scrambled data set and sort of more or less random gives you a better chance of having a nicely balanced tree where things aren't that far away, and you're guaranteed to find anything you're looking for within a small number of steps. So basically, you want to find different ways of minimizing the height of your tree. This tree over here has height 0, 1, 2, 3, height 3, right? The lowest is level 3 down here. Whereas this has height, however many things are in it, 1, 2, 3, 4, 5, 6, 7, 8, height 8, right? So you want to minimize our height to make an efficient tree. I'm not really planning on getting into the like ways of doing that. I think you guys study this in 1107. Is that right? Have you guys talked about like how to rebalance a tree?
Yeah, we do a lot of that.
Okay. Well, you don't need to learn that from me then. Um, oh, Ben asks a very good question. What if you have two data elements that are like equal to each other? What do you do? I'm honestly not sure. Like, so if there's another A in the data set, how do you handle that? Do you guys know?
I don't know the right way, but personal style for me would tell I just shove it to the left. And then the next guy might come along and say, what the heck did you do?
I think that makes sense. Just be like, just have like a default, like, well, if it's equal, send it to the left. What you could have as your rules is, no, you could say like, if X is less than or equal to Y, send left. And if X is greater than Y, send right. You know, something like that, where you just default to going left if it's equal. Yeah, that seems reasonable. Yep. So 1107. Yep, that's the class Nicholas was mentioning. That's fundamentals 2, right? That's where you guys learn that sort of thing. So yeah, this is one application of a tree structure, which you guys will work with in managing data. Let's learn another one. Go ahead and save this in here somewhere. Is it today? The 13th. Oops, I think I labeled my calculus class as the 12th. That's okay. Any other questions or comments? Is there anything you guys want to share on this topic for binary search trees? Or questions about it? Oh, I forgot. I was actually going to do something with this besides just talk about how to construct it and how to search through it. Let's actually just kind of get rid of that. What I want to do is take this opportunity, as long as we've got this thing here, to discuss tree traversal. So if you are storing a data set in a tree structure, how do you traverse through the tree? Meaning, how do you go through the tree and read off every single data element? Or if you want to iterate through that collection, like if you have to do something, if you have to go through and make a correction to every single data element, or if you want to like add in something to every single data element, how do you iterate through that data structure? Well, there are different ways of doing it, and these are called tree traversal algorithms. There's 3 I will show you. One is called pre-order, one is called in order, and one is post-order. So this is for a binary tree specifically, although the concept can be extended to trees with more than 2 children, like a ternary tree or a quaternary tree or something like that. So the order, the different possible orders here, pre, in, and post, refer to, with regards to a node and its left and right children, what order are you going to read those nodes? We're going to refer to these as self, left, and right. self, left, right. What order are you going to read them? Well, the pre-order says do self first and then do left and then do right. The in order says do left and then read your self value, the self value, and then do the right. And the post order says do left, then do right, and then do self. So as for the pre, in, and post, it refers to when the value of the node you're looking at is going to get read. Is it read before the children, between the children, or after the children? Okay, that's what the pre, in, and post refers to. We always read the children left first, right second. Why wouldn't you do that? I mean, like, why would you do it the other way, right? You might as well just have like a fixed left before right kind of order for the children. It's just a matter of where you put the self. So let's see. Let's read let's read the data from our binary search tree over here and see what we get for these three different orderings. So you always start at the root. Like I said, the root of the tree is your entry point to the data structure. Accessing the data structure is always done starting from the root. So, if with a pre-order traversal, the very first element that is read from the data structure is K, because when you access that node at the root, you read the self value first. Then you read then you go to the left node. And when you're on the left node, you start over with this ordering. Okay, so you say, again, based on the self left right order, with this node, the first data element we read is the H. And then we move to the left, and now we're down here. Okay, and then start over. We're going to read B. And then you move to the left, and you're down here. And then we read A. And then you would move to the left, but you can't. So as soon as you can't move left, then you've done self, you've done left. You can't do left, so you look to the right. Can you do right? No, you can't. And when you come to the end of this list of steps, self, left, right, you go back. And so now we are done with this node. This node is like checked off. It's finished. Its job of reading self, left, right is complete. And we go back to node B. For node B, self is done. We already did that. Left is now done because the entire left node has been read. And so now we move to the right and we read C, and we say, all right, C, do the job. Go through the checklist, node C, and node C first reads itself. There we go. And then it would read whatever is to the left of C, but there isn't anything there. Then it would read whatever is to the right of C, but there's nothing there. And so now it's done, and it returns to B. And now B already did self, B did left. Now B just finished doing right, and now B is done. So B is done, and B returns to H. Now H says, I did my self, I did my left. Now it's time for H to look to its right child. Right child reads J. It doesn't have a left, it doesn't have a right, so it's done. It goes back to H. Now H is done. H is done, and H returns to K. K says, I read myself. I've now finished reading my entire left subtree, right? So the entire subtree to the left of K is now done. It's all been read. And so now K says, time to read my right child. K finally turns to the right child and reads N. Then N reads its left child, which is M. M doesn't have any children. It goes back to N. N reads its right child, which is W, no children, so it goes back. So that guy's done, that guy's done. Now N is done. And then finally, we return to the root, and we're back at the root, back where we started, and it says, I'm done. And as soon as the root says I'm done, then the whole tree has been read and we have our data. Not in the same order we put it in. We put it in this sort of random order, and now it's in this order. So that's pre-order. In order produces a different ordering. For in order, you always read the left child first. So we start at K, but we don't write down K. We don't like read that data. We just go left. We don't read H, we just go left. We don't even read B, we just go left. We get to A would go left, except that it can't, there's nobody there. So it says, never mind. Then it reads itself. So it starts with A. The very first thing that is read is A. And then it would read its right child, but there's nobody there either. So it goes back. Now B says, all right, I'm done with my left subtree. Now we read B. And then we read C, right? Then B says, I'm done with myself. Now I go to the right. Now I read C. The first thing that the node C would do is read its left subchild, right? It wouldn't read itself first, right? Because you got to do left before you can do self. So the first thing C would do would read its left child, but there isn't one. So then it reads itself, and then it would read its right subchild, but there isn't one. So it goes back. And now B says, I'm done with my left. I read myself, and now I've read my right. So now I'm done, and I go back up to H. So the next thing we get is H. Oh, sorry, yeah, then H. And then H reads its right child, which is J. And then we go back up to K. We get K. K now moves to the right to N, but then N goes left first because the left is first, right? So the next thing read is the M. And then N can read itself, and then N reads to the right. So you'll see when we do this in order traversal, what we get is something which is in order, which is lovely. This is now alphabetical order, right? So the in order traversal of a binary search tree always produces the data ordered from smallest to largest by whatever ordering system you're using, like alphabetical in this case. Smallest to largest in alphabetical order. And then post order, any predictions on what you get if you do post order? That was kind of a stupid leading question because the answer is not reverse alphabetical order. There's no reverse alphabetical order. But what you just get a different version of you just get another different ordering. So these are just different ways to read through a tree structure. Now, you might, for this example, you might ask, well, like, what's the point of pre-order or post-order? Because in order seems like the best one. It's like, well, then now they're listed from smallest to largest. That seems good. The pre-order is kind of random, and the post-order is also kind of random. So what's the point of pre or post-order? Well, for the next example, pre and post-order are much more useful. Let's take a look at the next example. Okay, for the next example, we're not going to talk about reading in a data set that is like a bunch of letters or a bunch of numbers or something like that. Instead, we're going to talk about equations, or actually not equations necessarily, but although you could do this with equations, but I'm going to do it with a mathematical expression, an algebraic expression. Does that look familiar? Which algebraic expression is that? Which formula is that?
Quadratic.
Yeah, that's the famous quadratic formula, right? And I'm actually even going to do this as a 1 divided by 2. Okay. We're just going to do it with integers. And although they could be maybe, well, yeah, let's say they're going to be integers and operations. Okay. So how would a computer store this formula? It can't really do it like this, because the way this is written with the power like that and the all over 2a is like, it's sort of this like two-dimensional, the computers don't have a concept of superscript. They don't have a concept of like writing one thing over another thing. Computers don't deal with like this two-dimensional like paper, right? They deal with one-dimensional strings of inputs. So we need to, in order to make a formula like this meaningful or comprehensible to a computer, we need to convert it to a string. Okay, so in order to do that, we're going to need to use some more parentheses than we currently have here in order to like override order of operations and that sort of thing. Also, this negative b right here, in order to really clearly state what that is, I'm going to write that as -1 times b. Okay, so what we need to do is have numbers and operations and parentheses. So we have -1 times b plus, and then a parenthesis, b to the power 2. Okay, so there's the, I'm going to use that symbol for power. Okay, if you were using some data, or some programming languages, you might use ***, whatever. But I'm just going to use that one for this example. And then minus, and then what we're subtracting is 4 times a times c. Do I need parentheses around 4 times a times c? No. I shouldn't really need them around 4 times a times c, because order of operations is going to handle that. That's fine. We can have order of operations kind of programmed in potentially. Although what I do want to think about is what order the computer is actually going to multiply these numbers in, because computers can't do like 2 multiplications at once. The computer does have to specifically do one multiplication and then the other multiplication. Thankfully, because of the associative law, it doesn't really matter if we do it that way with those parentheses or this way. That doesn't really matter. So I'm going to do it that way. So that will come to an end. I need a parenthesis there. That gives me that whole expression, right? And then I need to raise it to a power. And the power I want to raise it to is 1 divided by 2. I have to put this in parentheses, the 1 divided by 2, because if I didn't have those parentheses, what it would do is it would just raise this to the power 1, because raising to the power 1 is, in order of operations, that exponent comes first. And then the entire result of that would then be divided by 2. And I don't want it to be that way. I want the 1/2 to be the actual exponent. So it goes in parentheses. Now, all of this needs to be in parentheses to be divided by 2a, which is 2 times a. But again, if you're dividing by something, we want our entire 2a, the entirety of that 2a, to be in the denominator. If I just type it in like this, and you guys may be very familiar with this from typing things into your calculator, like if you have a TI-83, especially the old ones that don't have the vertical like fraction format, this will get evaluated, and then that, because the divisions and multiplications will be evaluated in order, right? So we would, in order for it to be legible to a computer or a calculator, in order for it to be correctly interpreted the way we intended, we've got to put parentheses around our 2 times a. Okay, so there we go. So that's our first step, is storing this as a storing this as a string. Okay, so this is our string representation. With parentheses required. Okay. Now we can read in this string. Okay. And we can read it. We're not going to read it in this order. We're not going to read it in this. Actually, so I said read in the string, but actually that's not quite. That's not exactly what we're going to do. We are going to represent this. We're going to represent this formula in a tree structure. And the fundamental concept of this comes from the fact that we are using pluses, minuses, multiplications, and divisions, and exponentiation. And all of those are binary operations, which means that they all have the format input, and then a symbol, and then another input. Okay, they all have that. And so the way we are going to do this is in a binary tree is to have the parent node assign. We're going to assign the operation to the parent node, and then we're going to have the first input assigned to the left child, and the second input assigned to the right child. So in a way, the inputs are A and B, and the operation returns the output value to its parent, whatever its parent might be. That's how you want to think about this. So really this is more like this is a function of A and B, and that function will return the value A operated with B, whatever that operation is, whether it's whichever of those binary operations we might be using, whether it's adding them or multiplying them or dividing A by B or whatever. Okay. That's how we want to think of this, as a function like that. Now, looking at our quadratic formula, that whole quadratic formula up there, which I'm accidentally writing like way too big here, so I'm just going to make everything a bit smaller. Okay, looking at our whole quadratic formula up there, the overall picture is a fraction. That divided by that. Okay. Overall picture here is a fraction. So the overall function that's happening is a division. So this is our root right here. The root is going to be what is returned, the value returned by that division operation. That's like the last thing you would do, right? On the left of that division operation is going to be that entire thing. And because that's the numerator. And on the right is going to be this thing, which is the denominator. Okay, so let's kind of spread that out a little bit, because the left and the right here, I need to make sure I just give myself sufficient space to represent this. Okay, so we're going to have left, we're going to have right. Okay. So over on the, let's do the right side first, because the right side's a little simpler. Over on the right side, I'm going to change my mind again. I'm sorry. This is going to have to be, oh crap, what just happened? This is just going to have to be over here. Okay. Just going to have to be over there to make it work. Okay, so over on the right side, we have a fairly simple situation, because over on the right side, we have to have 2 times A. So what we're going to be plugging in as the second input, the denominator, is the result of a multiplication. So this node on the right child here is actually going to be the times operation, and its left child is 2, and its right child is A. Okay, so some of the nodes are going to be operators, right? And so sometimes sometimes the inputs to an operator are operators themselves. Does that make sense? Because the entire input is the result of an operation. Same is true on the left side. what is going on the left side? What operation should go here? If we look through this entire left side, what is the overall operation that is happening there? That is the result of a what? Is it a multiplication? Is it an exponentiation, a division, an addition, a subtraction? We have all of those different things happening. Is it exponentiation? If it were like, if this was in parentheses and we were raising all of that to the power 1/2, then it would be exponentiation, and you guys would be right. But it's not. There are no parentheses there. The exponentiation only applies to that much. With that being the other term, the overall operation on the left side there in the numerator is actually addition. So we want to put addition right here in our tree. Addition. And then the addition is going to have a left child and a right child. The left child of the addition is -1 times b, right? So because the first term in the addition is -1 times b, that's going to look a lot like this one, where it's a times with a -1 on the left and a b on the right, right? Now, for the right child of the addition, the second thing we're adding, this one is the overall result of an exponentiation operation, right? So this is where we get to use the exponentiation with a left and a right. That's that exponentiation. So now we've got to look at our left and right side of that exponentiation there. So we're looking at, that's the left side, what's in there, and the right side is this. The right side is pretty easy. Let's do the right side real quick. That is just 1 divided by 2. So on the right side, we'll do a division with a 1 on the left and a 2 on the right. Right? It's nice and simple. And then the left input to that exponentiation operation is this. So what is that? Well, that b squared minus 4ac, what is that? Overall, it's a result of what operation? We've got several operators in here, right? Let's see if we can figure it out. There's an exponentiation here, there's a subtraction, there is a multiplication and another multiplication. But which one is the overall thing that's happening here? It's subtraction. That's right. You guys got it. So it's subtraction because it's this minus this, really. So yeah, so the next node here is a subtraction node, and it's going to have a left and a right child. Its left child is b squared. So the left child is the result of an exponentiation operation with a b in the base and a 2 in the exponent. And the right child over here is the result of a multiplication. And so this now is where the order of that multiplication matters. So the way that I have it written here is like 4 times something, and the other something is a times c. So with those parentheses, this portion of the tree will look like multiplication with a 4 on the left and another multiplication on the right. And that multiplication has an A on the left and a C on the right. Like that. So now, this tree represents the quadratic formula. This is our quadratic formula tree. Okay. And now, if we apply one of our tree traversal algorithms to this, we will discover what is called one of these sort of alternate notations for algebraic formulas. So there is a notation called Polish notation, which you get by doing a pre-order traversal of this formula tree. So if we do pre-order traversal, let's practice that pre-order traversal again. We just have 3 minutes here. This should be fine. Start from the top. You say, all right, we're going to read the left node first. Or sorry, no, wait. No, sorry. Pre-order is self, right? Pre-order is self and then left and then right. Right? So pre-order says, okay, we read the self first. So the first thing we read is slash. And then we go to the left and we read plus. And then we go to the left and read star. And then we go to the left and read -1. And then we go to the right and read B. And then we're done with that. So we go back up, right? So it's always left, 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 left. And we're reading self, 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 and then left. And then when we're done with left, remember, we go back and read right. And then when we're done with left, so now we're done with left, we go back to the plus here and read it's right. Okay, so we've gone down here. Let me kind of draw out the traversal. It's nice to kind of draw it out. We've gone down here, gone up, we've gone to the right. Now we go back. Now we're going to go down the right path. So we're going to read that exponentiation operation. And then we go down its left path. And we start going all the way down its left path down here. So we go, we'll read minus, and then we'll read exponent again, and then we'll read B. And then B doesn't have a left, so we go back, we read the right is 2, right? So we kind of went like this, we went to the right, and now we go back, and now we go to the right. We read star, and then we read its left, right? Because we always go left first before right. So we're going to read 4. That's a 4. Not hard to tell. Here we go. We read 4, and then we read the right, star, and then A, and then C. And I'm running out of space here, so let's do a little. Oops. Let's do a little rearrangement here. And I keep on going around in my pre-order traversal. I read A and then I read C. So now I'm done with star. I'm done with that star. I'm done with that subtraction, and I come all the way back up to this exponentiation node, and then I go down the right path. And I start going around this thing. So I'll read another division, a 1, and then a 2. Back all the way back up. We're finally completely done with the left subtree, and we start reading the right tree. And the last few things we read are star, 2, and then A. And then we're done. So star, 2A, and then done. And this is called Polish notation. And it is an interesting notation for algebraic formulas that doesn't require any parentheses. If you read this, it's possible for a computer to interpret this and reconstruct this diagram from that interpretation, from that string, and then have a correct understanding of the formula involved here. Every time it reads an operation, it is expecting 2 inputs, and if one of those inputs is an operation, it just expects 2 inputs for that. And so it's this beautiful kind of. It looks like this nonsensical string of symbols, but it actually is a nice compressed, efficient representation of a formula without the need for any parentheses and without the need for any order of operations, which is going to. There's no hidden rules like order of operations here. Okay, everything is just clearly laid out without needing to follow an order of operations. You just do all the binary operations in the order they're stated there, where it's operation, input, input. So it's pretty cool. So yeah, so as far as programming computers to do algebra, using Polish notation is a much more natural way to do it for a computer. It doesn't require any extra rules or extra understanding. It just, and also like, it's just a string of characters. So it's super easy to code in and feed into a computer and have it interpret. So that's Polish notation. If you do a post-order traversal of this formula tree, what you get is this thing called reverse Polish notation, where it's input operation in that order. Two inputs first, and then the operation at the end, which is, it's fine. Whether you're using Polish notation or reverse Polish notation, they are equally useful. I don't think either one has a particular value over the other. Okay, so that's it. That's been it for tree applications today, folks, and traversal methods. I think that's it for trees. So we'll see you tomorrow. No, it's Thursday. See you Monday, everybody. We get to start a new subject on Monday.
Have a great weekend.
Thank you. You too. Bye, everyone.